from outer stars to inner binaries. That these processes are expected, and when they occur, they can do interesting things. So let's go on now and talk about mass transfer from a giant to a compact object binary. Well, we can start with the inner binary containing any combination of compact objects. The donor has to be in a wide orbit, and there are stability conditions for the orbits in a hierarchical triple. So we have to put it far enough out that it satisfies those stability conditions. Typically, just to have an order of magnitude estimate in your mind, the ratio of the period should be about 5 or more, okay? Inner to outer period.
What sets that ratio minimum 5? What sets that ratio?
Well, it's very difficult to say. Stability in these systems is rather difficult to establish. So mostly people have done simulations, but the basic idea is that you'd like the inner binary and the outer binary to be able to essentially be independent, although they may.
The outer single.
Well, the binary that's composed of the inner binary and the outer star, and the binary that's composed of the objects in the inner binary, that those should be more or less independent, although you can have interactions where angular momentum, for example, is exchanged and the Kozai-Lidov effect can be active. By the way, there's been a lot of work on Kozai-Lidov, especially as the presence of the outer star influences the dynamics of the inner binary. But I'm not going to talk about that today. I'm going to be focusing on mass transfer, which would be the more important effect if it occurs. So during times of mass transfer, that should dominate.
So is there an outer limit? I mean, you have 5 to keep it stable, but how about the limit for making sure you have mass transfer nonetheless?
That's a beautiful question. And that's exactly what I had to figure out. I didn't know whether that was the case. So what I actually did is to create systems on the computer. So I created an inner binary, and the masses of the inner binary started at about 0.6 and went up to 7. So in other words, these ranged from carbon-oxygen white dwarfs to the types of black holes we have typically found in X-ray binaries. And I let their separation be determined by choosing a time to merger from a logarithmic distribution ranging from 10 to the 8 years to 10 to the 12 years. And that set their separation. I assumed the orbits were circular. Then I selected an outer star. Most of these outer stars were less than 9 solar masses, but I did allow them to go up to 20 solar masses. I chose the inner boundary for possible orbits according to the condition of dynamical stability, but I let the outer boundary be far wider than was reasonable because the simulations would tell me where mass transfer happened and where it didn't happen. I was considering only giants as the donor, and I started them with a core mass of 0.2 and made sure they didn't fill their Roche lobe out till that point. And then I evolved the stellar core, and because of the formalism that was developed originally by Paczynski, when you know the core mass of stars in this mass range, you also know their radius and their luminosity. And you can use a Reimer's wind formalism to tell you how much winds they are. But to make that formalism more realistic, I modified it so that it also leads to the correct final mass for each star. And so that allowed me to derive a formula for the mass in terms of the core mass. So for each value of the core mass, we know how big the star is, how luminous it is, what its mass is, and what m dot is. And of course, this is assuming that this formalism works, but it's not bad. People have compared this to the results of simulations like the MESA, from the MESA code.
Sorry, as not a star person, how is the core mass related to the main sequence mass?
How is the core mass related to?
Like the mass, like the total mass of the star on the main sequence.
Well, on the main sequence, it's not. So you choose the initial main sequence mass, and then in this case, I didn't start evolving the star at that point. I waited until it already had an evolved core. Once it has an evolved core, then it's the core that determines the stellar properties, such as the luminosity and radius, which help to determine the amount of winds. So if you can compute the winds at every time, and you know when you started, then you know how much mass you have left at that time. And this was just nice because you have analytic formulae to derive to, of course you run it through a computer code, but you have a nice analytic formulae as your input.
C0?
C0 was the core mass I started with, which in this case was 0.2. Now the things that are less well known have to do with mass flow. So the question is, how much of the mass that's lost by the donor is actually comes under the gravitational influence of the inner binary? I said that was a fraction gamma, and gamma is proportional to one constant kappa, and this functional form has the following effect. It means if this binary is very far from the star, then the amount of, the fraction of the mass that you intercept is 1 over r squared. But if you're close, it's 1 over r. And that corresponds to focused winds, which emerge from both theoretical and observational considerations. So this is appropriate for focused winds, but this kappa is not really known. The other thing that's not really known is how much angular momentum is carried away by mass that exits the system. So I had to make assumptions about the specific angular momentum carried by mass exiting from the inner binary and also exiting from the outer star without ever getting to the inner binary. So each simulation had 3 quantities that encapsulate our uncertainty about the important physics involved with mass flowing within and from the system. So one question we have is, do the results depend on these parameters? Like, are there some parameters for which you get interesting effects and others for which you don't? Now, I think what I had to do, of course, is to assume that the mass that was captured, some fraction of it would be captured by one star, but maybe not all of it retained. Beta 2 was the amount retained. The second star then had a shot, and the rest of the mass exits the system. There are many ways of doing this, and I tried many ways of doing it. If the donor comes to fill its Roche load, so in many cases this donor may never fill its Roche load. It may only give mass through winds. But if it's close enough and if it expands enough, it may fill its Roche load. And then if it's more massive than the inner binary, it will very likely lead to a common envelope. So you could either have that type of unstable situation, or you could have the inner binary continuing to have a steady flow of mass from the outer star. Let me show you some of the evolutions. So this is showing you in red what's happening with winds. And this is, in blue, is the amount of mass per unit time that is going on into the inner binary. In this case, the primary star has 6 solar masses, and the second star, this is in the inner binary, has 0.9 solar masses. It's a carbon-oxygen white dwarf. But there's a very massive donor, and in this case, if you take a look at the accretor mass, now looking at the 0.9 solar mass star, you can see that at least in several cases, it achieves the Chandrasekhar mass. And so it would explode as a type 1a supernova. The other interesting thing is that even when mass is not being actively added to one of the stars at a high enough rate to show up in this graph, angular momentum loss as mass exits the system takes a toll, in that it decreases the orbital period of the inner binary, and it also decreases the time to merger. Each of these systems started out with a time to merger larger than the Hubble time, and each of them ended up merging within a Hubble time. Here's a similar set of evolutions, in this case starting with a neutron star of 1.6 solar masses. And again, in at least 3 of these evolutions, the neutron star went over 2.2 solar masses, indicating that it probably would have collapsed to become a black hole. Okay, so now the point was not to evolve a few stars, but to actually understand how initial conditions map to final conditions. So we ran many simulations. And here is a portion of the results. These parameters are each, this is an angular momentum parameter for the outer binary, that is the one of the outer star and the inner binary. This is simply for the inner binary. Actually, I have that reversed. And this is the fraction of mass that could be retained. And I assume that even if you're filling your Roche lobe, in general, only 50% of the mass could be retained, but there was one simulation in which it was only 35 and one in which it was 75. And then this number is the number of systems whose time to merger declined by a factor of 2 or more. Out of 33